Hi everyone, it's Wednesday, which means it's time for another live stream. Hopefully the sound issues have all been worked out. I've done some testing. I think the sound is okay. OG Benchmarks, help me out here. Just let me know if my sound is not good or if it's actually on and if it's at an appropriate level. Okay, audio is good. Fantastic. Okay, so we are going to work our mole ratio problems that I wanted to do last week until nobody could hear me. So let's go ahead and get started. Okay, so to start this off, I actually am going to not jump into immediately a chemical equation, but a situation that hopefully you have run across in your everyday life. We are going to talk about cheese sandwiches. And I did this because it's simple instead of having a lot of ingredients in it. Okay, so this is cheese sandwiches, part one. So we have a cheese sandwich is 2 slices of bread and 1 slice of cheese. Again, we're making very simple sandwiches here. Write a chemical equation for the statement and then balance that equation. So what I really want to tie this to is a lot of students feel like, oh, stoichiometry, this is something brand new. I've never done this ever before and it's really difficult. But I want to show you that actually a lot of these concepts you're very familiar and very comfortable with. We just need to take that comfort and that familiarity and apply it to chemical equations. Okay, so I'm going to do part A here. Okay, so we have, again, simple sandwich, cheese sandwich. We have bread plus cheese gives us a sandwich. Okay, so this is our chemical equation. We have 2 reactants and we have 1 product. Now we want to balance this equation, and this is where we put in what we call our stoichiometric coefficients, or how much of each of this ingredient do you need? Well, we need 2 slices of bread to make a sandwich, so I'm going to put a 2 here. We only need 1 piece of cheese. I'm going to go ahead and put a 1 there, even though technically you do not have to put a 1 there. If there's nothing written there, it's assumed to be a 1. But let's just be clear, so I'm going to put a 1 there, and that gives me 1 sandwich. So this is now not only a chemical equation, but a balanced chemical equation. So we are going to use this chemical equation to answer some stoichiometry questions about making cheese sandwiches. So let's take a look at part B. How many sandwiches can you make with 10 slices of bread? Again, because I'm tying this to the real world, you don't actually have to write anything down. You're like, 10 slices of bread. I can make 5 sandwiches. It's not a big deal. But I want to tie it to the actual math because, again, this is the math that we're going to mimic when we're dealing with chemical equations. So what I do is I start with what I've been given. I have been given 10, instead of saying slices, this is just going to take me forever to write. I'm going to say 10 bread. And I want to predict sandwiches. Well, what I'm going to do is I'm going to use the mole ratio, if you will, between bread and sandwich. And what I mean by that is the numbers written in front of these. So you can see I have a 2 written in front of bread and a 1 written in front of sandwich. This is what I would call the mole ratio of bread to sandwich. Now, when we're doing this conversion, because this is really a conversion, you can think of these as all dimensional analysis problems, I want to make sure that my bread, my unit that is bread, cancels out. So I'm going to put 2 bread in the denominator, goes to 1 sandwich. So again, this whole thing is called the mole ratio. Let me write that down. This is the mole ratio. And I get it from the balanced chemical equation. This 2 comes from this 2 right here. This 1 comes from that one right there. So the mole ratio between bread to sandwich always remains the same. It's not going to change no matter how much bread you have, no matter how many sandwiches you want to make. It's always going to be a 2-to-1 ratio, which you already know, right? Okay, but this is where we get now our 5 sandwiches. So what I want to show here is you can see the bread cancels, and for the math, we just did 10 divided by 2, and then you could argue that you then multiplied by 1, but of course that doesn't change anything. And this is why we get 5 sandwiches. So the math that you did in your head without even thinking about it, without even worrying about it, is exactly the kind of math that we're going to do in our mole ratios. Okay, so we're going to do a couple more of these. Again, you're going to know the answer before you actually calculate the answer, but that is a good thing because I want you to recognize the skills that you already have in doing stoichiometry. Okay, so that was B. Let's go ahead and do C. So C reads, how many slices of bread do you need to make 25 sandwiches? Again, you already know this, but let's go ahead and work through this. Okay, so we're going to start with what we're given. We were given 25 sandwiches. So this is 25 sandwich. Now, we want to move between sandwich and bread. So we need the mole ratio between sandwich and bread again, which is the same thing. It's just a 2 to 1. Or you can think of this as a 1 to 2 ratio. It doesn't matter how you think about it. Again, you've already done this in your head, and you know that it doesn't work out evenly, but that's all right. We just want to see how the math plays out when we write it down. So I'm still using the same ratio here, but again, this time I want my unit of sandwich to cancel. So I'm going to put 1 sandwich in the bottom. In the denominator, and 2 bread in the numerator. Okay, so what this does is your sandwich cancels and you're left with bread. So this is the math that you already did in your head. So you already knew it was going to be 50 before we started, but this is how it works out using the mole ratio. Okay, so let's put our answer down here. So this is 50 sandwich. Okay, so let's go on to part D here. If you have 3 slices of cheese, how many pieces of bread do you need? How many sandwiches can you make? Okay, so this is a situation where we're comparing 2 reactants. So we know cheese and we want to know our other reactants. So mole ratios work not just from reactants to products or products to reactants, but you can compare 2 reactants and you can also compare 2 products. It all goes back to our balanced chemical equation, which we already have. Okay, so I am going to actually give myself another page here because I need more space. And let's rewrite our balanced chemical equation up at the top. 2 bread plus 1 cheese yields 1 sandwich. Okay, so going back, let's reread this again. I have 3 slices of cheese, and I want to compare that to bread. And then I want to compare that to the sandwiches. So let's go from cheese to bread first. Again, you've already done this in your head, but I want to show how the math that you're doing in your head is correct and it actually has a form that we can write down and then compare again when we do stoichiometry. Okay, so I was writing down cheese. I lost myself there. Okay, so because we're comparing cheese and bread this time, we have a different, well, it's the same number, but still we're comparing cheese and bread. So our mole ratio again is 1 to 2, but we're looking at 2 different, I don't want to say molecules, components here. So this time I want cheese to cancel. So I'm going to put 1 cheese here in the denominator. And I want to go to bread. I want to know bread, so I'm going to put bread in the numerator. And what this does is it makes the unit cheese cancel, and now I've got bread. And so, of course, this equals 6 bread, which you, again, already knew. You didn't have to work to make this math happen, but I want to show you what the math that you're doing in your head so easily is actually doing on paper. And now we wanted to predict how many sandwiches we're going to make. So we're going to do another calculation. I'm still starting with my 3 slices of cheese. This time I have a different mole ratio. So I'm comparing cheese, which is 1, and sandwich, which is 1. So this is a 1 to 1 ratio. But I still want to set it up so that my units cancel again, even though I know what the number is that I'm going to get. I want to make sure that my cheese unit cancels. And I'm left with sandwich. And of course, this gives me 3 sandwiches. 3 sandwich. Okay. Let me show you how my units cancel. So my cheese is canceled, and now I'm left with sandwich. So again, these are really, really easy, I know, and that is a good thing because I want them to be very easy. Okay, so one more. We're going to do part E. To make 8 sandwiches, how many slices of bread and how many pieces of cheese do you need? So this time we're going to take a product and we're going to predict how much of each reactant we need. Again, all we need is our balanced chemical equation, and we've got mole ratios for all of this. So we're going to work with 2 different mole ratios. So we're starting with sandwich, and first we're going to predict bread, and then we're going to go sandwich to cheese. So we're dealing with a 1-to-2 ratio and then a 1-to-1 ratio. Again, you've already done this math in your head. I know you just read it and did it, but let's write it down and see how it works out. Okay, so we've got 8 sandwiches. So let's start with 8 sandwich. And it doesn't matter which one you predict first. I think the problem asked me to predict bread first, so I'm going to go ahead with bread. So again, this is where my mole ratio goes, and it's 1-to-2. I want to make sure that my sandwich unit cancels. So I'm going to have 1 sandwich in the denominator, and this is going to 2 bread in the numerator, which of course gives me 4 bread. Oh, sorry, I divided. This is why we write things down. So 8 times 2 is 16. But you can also see, with just that mistake that I made there, how if you're trying to do these stoichiometry problems with mole ratios and with actual reactants and products, if you're not writing them down, if you're like, I can just do this in my head, be careful, because you might end up doing just what I did there. I even wrote down the right thing, but in my head I did the math wrong. So it's always helpful to write it down, make sure units cancel, and make sure you're doing the math correctly. Okay, that was bread. Let's also predict cheese. So this time I'm going to take my 8 sandwiches, and I want to know how much cheese I need. So this is a different mole ratio, of course, because I'm comparing sandwich to cheese. This is a 1-to-1 mole ratio. But still, sandwich cancels. I'm left with cheese. And of course, I need 8 slices of cheese for this. Okay, so hopefully you found that very, very easy. I actually am hoping that you found it just a little bit boring because it was so easy, because I want you to take this really boring, this really easy math, and we are going to apply it to chemical equations. Okay. All right, so it doesn't look like there are any questions, which is good. I don't want there to be any questions. I want that to be easy, easy, easy. Okay, so here we have a balanced chemical equation, which means we already have mole ratios ready to be put into place. So if you have trouble balancing chemical equations, 2 weeks ago I did a live stream of just balancing chemical equations. But for this live stream, we're going to start with balancing equations so we can focus on mole ratios. Okay, so let's read part A here. How many moles of aluminum chloride is formed when 2 moles of aluminum react completely? Okay, so first I want to identify what 2 molecules am I comparing and what is the mole ratio. So aluminum chloride, of course, is right here, and it's got a 2 in front of it. That is its stoichiometric coefficient. And I'm comparing it to aluminum, which is right here. It also has a 2. Now, your mole ratio is only dependent on your balanced chemical equation. Again, it doesn't matter that I have 2 moles of aluminum that I started with. That is completely independent of either this 2 or that 2 there. They just happen to be the same number. So let's start with what we were given. We were given 2 moles of aluminum. Okay, so this is part A. We have 2 moles of aluminum. Again, this is all dimensional analysis here. We want some units to cancel and we want other units to remain. In this case, I want my moles of aluminum to cancel. I want to get rid of those. So I'm just going to go ahead and write my units here, moles of aluminum. That's what I'm canceling. I want to get rid of it. What am I trying to predict, or where am I trying to go? I'm trying to go to aluminum chloride right here. That's what I'm trying to predict. So, and specifically moles of aluminum chloride. So I'm going to go moles of aluminum chloride. Okay, now that I have my units and I know they're in the right place, I'm going to go for my numbers. I'm going for my mole ratio here. So for moles of aluminum, I'm going right here, and there is a 2 in front of it. So I'm going to put a 2 right there. For my aluminum chloride right here, again, there is a 2 in front of it. So I put a 2 here. Again, this is my mole ratio. I'm going to write that down. So my mole ratio between aluminum and aluminum chloride is 2 to 2, or you can also think of this as a 1 to 1 ratio. So you can reduce it in your head if you want, or you can keep it like I've written it down here, because mathematically it's going to work out the same no matter what you do. So you can do 2 times 2 divided by 2, or just know that you're really multiplying by 1, which is the same thing. So this is going to give me 2 moles of aluminum chloride. Okay, so let's show how my moles of aluminum have canceled there. Again, I hope you find these calculations easy, because I really want you to focus on the concepts that are behind them and know where these numbers are coming from that I'm plugging in and why I'm putting them in either the denominator or the numerator. Okay, so that's A. Let's go ahead and go to B. All right, so B asks how many moles of hydrogen gas will be formed when 3.75 moles of hydrochloric acid react completely. So again, I want to identify the two molecules I'm working with. Okay, so I am starting with 3.75 moles of hydrochloric acid. That's right here. And I'm going to moles of hydrogen gas there. So I'm taking a reactant and comparing it to a product. So my mole ratio is going to be 6 to 3 here. But let's write it down. So starting with what we were given, we were given 3.75 moles of hydrochloric acid. All right. Now I'm going to put my mole ratio in. But before I put numbers in, I want to put units in to make sure things cancel like I want. I want to make sure my moles of hydrochloric acid cancel. So that's going in the denominator here. The problem is asking me to predict moles of hydrogen gas. So my moles of H2 are going to go in my numerator. That way I know that I have my units set up right. And now I'm just going to put the numbers in based on the balanced chemical equation. Again, this is my mole ratio. So for my hydrochloric acid, what number's in front of it? There's a 6. So I'm going to put a 6 right here. And for my hydrogen gas right here, there's a 3 in front of it. So I'm going to put a 3 here. Again, this is my mole ratio. It's purely based on the balanced chemical equation. It's never going to change. It doesn't matter how many moles that you start with or how many moles you finish with it. The mole ratio is always 3 to 6 or 6 to 3. Of course, you can reduce this one as well. Mathematically, it does not matter. Okay, so if I have 3.75 multiplied by 3 divided by 6, I am getting 1.88 moles of hydrogen gas. Again, let me show how my units cancel. See how the moles of hydrochloric acid have canceled, and I'm left with moles of H2. Okay, so hopefully this is starting to get a little bit easier and make sense as to where these numbers are coming from and why I'm putting things in where I'm putting things in. Okay, so let's do C here. Oops, that C is a little janky. All right. To produce 0.85 moles of hydrogen gas, how many moles of aluminum and hydrochloric acid is needed? So this is really a two-part problem. I'm going to do two different calculations for this problem. First, I'll predict moles of aluminum, and then I'll predict moles of hydrochloric acid. So again, starting with what we were given the 0.85 moles of hydrogen gas. Okay, so I know I want to cancel my moles of hydrogen gas. And for the first part, I'm going to predict moles of aluminum. So I'm going to put that in the numerator. Now let me find my mole ratio for these two molecules. So for hydrogen, I've got a 3 up here. So I put a 3 there. And for, oops, that's supposed to be aluminum. I dropped my L there. For my aluminum, there's a 2 in front of it. So there is my 2. Again, making sure that I have canceled properly. And so 0.85 times 2 divided by 3, I did that. Where is that? 0.57 moles of aluminum. Okay, let's now predict moles of hydrochloric acid. So a lot of times I see students if they read a problem like this, they're trying to do both of these questions in one calculation. You're not going to do these in one calculation. These do need to be separate calculations because you have different mole ratios for different molecules. So still starting with my 0.85 moles of hydrogen, because that's what the problem gave me. I still want my moles of hydrogen to cancel, but this time I'm trying to predict moles of hydrochloric acid. Okay, so let's get that mole ratio. In front of my hydrogen, again, is a 3, and in front of my hydrochloric acid is a 6. I am going to have to squeeze this up here. It's going to go right up here. And I have 1.7 moles of hydrochloric acid. That is an HCl. That looked kind of like a 4. Okay, so just double check, make sure things canceled like you want. So our moles of H2 canceled, and now I'm left with moles of hydrochloric acid. Okay, part D, I'm going to need another page again. So let me give myself another page. All right, there we go. Let me just rewrite the balanced chemical equation up top here. So we've got it, because this is our most important piece of information, is our balanced chemical equation. This is also why when you're doing these problems, you do want to make sure first that you have a balanced chemical equation, because if you haven't balanced your chemical equation, then unless your equation is all one-to-one, your numbers are going to be all wrong for predicting either products or reactants or any of these. Okay, so let's go on to part D here. How many moles of aluminum is needed to react completely with 12.2 moles of hydrochloric acid? Okay, so in this case, I'm taking moles of hydrochloric acid, which is a reactant, and I'm predicting how much of my other reactant do I need. Okay, let's go ahead and do this. So we're starting with 12.2 moles of HCl. Just want to make sure I get these numbers transferred over right. Okay, so there is our 12.2 moles of hydrochloric acid. We are trying to go to aluminum, but first I want to make sure that my hydrochloric acid cancels, and now I'm going to moles of aluminum. All right, so that's my units in. Now let's put my numbers in. So my number in front of my hydrochloric acid, of course, is a 6, and my aluminum is a 2. This will make sure that my moles of hydrochloric acid cancel. Now I'm left with moles of aluminum, which is exactly what the problem asked me. And I'm going to get 4.1 moles of aluminum. Was that it for that one? I think that was just it for that one. Yes, it's just moles of aluminum. Okay, so you can see in all of these equations, there are 1, 2, 3, 4 molecules here. So I have a lot of different mole ratios. I can compare aluminum to any of these 3. I can compare hydrochloric acid to any of these 3. As long as you've got your balanced chemical equation, you've got your mole ratio for any molecule in that chemical equation compared to any other molecule in that chemical equation. Okay, let's make sure there are no questions. All right, so no questions. So this is fantastic. So let's keep trucking here. All right, so now we have a different, again, balanced chemical equation. And so we've got a different mole ratio for all of these reactants. Okay, but our method stays the same even though our numbers are going to change a lot. Okay, so for part A is if 1.90 times 10 to the third moles of iron reacts completely, how many moles of iron 3 oxide are formed? So in this case, I'm going to compare moles of iron with moles of iron oxide. All right, let's write down what we were given. We're given 1.90 times 10 to the third moles of iron. And we want to convert that into moles of iron 3 oxide. So I want to make sure my moles of iron cancel. So I'm going to put my moles of iron in the denominator, and I'm going to iron 3 oxide, or specifically moles of iron 3 oxide. So Fe2O3. Now I just need to put my mole ratio in. So for my iron, there's a 6 in front of it. So a 6 goes here with my moles of iron. For my iron 3 oxide, I have a 3 in front of that. So again, my stoichiometric ratio, again, you can think of this as 6 to 3 or 3 to 6, whichever way makes the most sense to you. Just make sure that your units cancel like you want. And now we can get our answer, which is 9.50 times 10 to the third moles of iron 3 oxide. Okay, so hopefully pretty simple, pretty straightforward. Let's keep going. Let's do part B. Okay, so part B reads how many moles of oxygen gas are needed when 0.975 moles of iron react completely. Okay, so we're starting with moles of iron. We're trying to get moles of oxygen. So in this case, we're comparing two reactants, but it's fine. We have our balanced chemical equation. That doesn't really matter. It's just kind of interesting to note. Start with what we were given. We were given 0.975 moles of iron. Okay, let's get units in. I know I want my moles of iron to cancel, so they go in the denominator. And this time I'm trying to get to moles of O2, so that goes in the numerator. Now let's get our numbers in from our balanced chemical equation. So in front of my iron is a 6, and in front of my O2 is a 2, so that is my mole ratio. Let's make sure my units cancel. My moles of iron cancel. Now I have moles of oxygen. And this is 0.325 moles of oxygen. Okay, so hopefully these are getting easier and easier for you. And now, oh, okay, that should be C, but it actually says it's D, so I'm going to put D here. Apparently we skipped over C. A reaction produces 2.15 moles of iron 3 oxide. How many moles of iron reacted and how many moles of oxygen reacted? So this is a case where we know the product, and I want to figure out how much of each of my reactants reacted, how many moles reacted. Again, this is two separate calculations, not just one. I'll predict moles of iron first because, I don't know, why not? 2.15 moles of iron oxide. Okay. So I want to make sure my moles of iron oxide, or sorry, iron 3 oxide cancel, and I am predicting moles of iron. So we have moles of iron. Now let's get our numbers in from the balanced chemical equation. Iron oxide, there's a 3. In front of iron, I have a 6. So now I'm ready to plug and chug. 4.30 moles of iron. And then how many moles of oxygen reacted? We've got 2.15 moles of Fe2O3. I'm going to have to crunch a little bit, sorry. Okay, so I know I want my moles of Fe2O3 to cancel, and now I'm predicting moles of oxygen. Okay, so let's get my mole ratio in. I have a 3 in front of here, and I have a 2 in front of here. Again, showing that my moles of iron oxide cancel. I did not do this calculation. Okay, so because I don't trust myself to do that calculation in my head, I'm going to grab my calculator. So this is 2.15 times 2 divided by 3. I am getting 1.43 moles of O2. Okay. All right, so that's it for this one. Okay, looks like there are no questions, which is totally fine. For the next part, I want to talk about limiting reactants, but we're still going to stay in moles. We're still going to keep it really simple mathematically, and we're going to work just on the concept. Okay, so we're going back to our cheese sandwiches because, again, I think it's just a really good example of how the math is actually going to work and how you have done stoichiometry before and you've done it very easily. We just need to take those skills and apply it to chemicals instead of, well, in this case, bread and cheese. Okay, so rewrite your balanced chemical equation for making a cheese sandwich. So let's go ahead and get that down. We know that we need 2 slices of bread plus 1 slice of cheese, and that gives us 1 sandwich. Okay, that's great. Now we know all of our mole ratios. Okay, so the question part B reads, if you have 3 slices of bread and 1 slice of cheese, how many sandwiches can you make? So we're going to go to sandwiches and then say, do you have any leftover ingredients? And if so, how much do you have? Again, you have just done this in your head and you know what you have left over, but I want to show you mathematically on the page what you just did very easily in your head, because this is how you do limiting reactant problems. Okay, so what I'm going to do is I'm going to say, all right, I've got 3 slices of bread. If I have 3 slices of bread, and don't worry about the cheese right now, if I have 3 slices of bread, how many sandwiches can I make? All right, so this is part B here. So if I have 3 bread, how many sandwiches will that bread allow me to make? Okay, so I know that bread is the unit I want to cancel, and I'm going to, cheese. I was saying sandwiches. That is my fault. If I am going to use 3 slices of bread, how many slices of cheese do I need? Okay, so there's a 2 in front of the bread here. There's a 1 in front of the cheese. Oops, let me show how this cancels. So bread cancels. So here's my cheese, and I need 1.5 slices of cheese. All right, so this is cheese needed. So again, if I'm going to use up all of those 3 slices of bread, how many slices of cheese do I need? Well, I need 1.5 slices of cheese. Do I have 1.5 slices of cheese? Well, let's go back to the problem. And if I go back to the problem, I can see that I only have 1 slice of cheese. So I do not have enough, or let's just say not enough. Not enough. So I'm going to run out of cheese first, which you already knew, but I'm going to run out of cheese first, and that makes cheese my limiting reactant. So that is limiting for me in this problem. But what if you hadn't chosen to say, well, what if I use up all my bread? What if you had decided to test in your cheese and see if you use up all your cheese, how much bread? So when you run these, what I call theoretical calculations, or sometimes they're called test equations, you can run them on both reactants, and they should both point you to the same limiting reactant. So if you do these calculations, and one calculation is pointing you to reactant A, and one calculation is pointing you to reactant B, go back and double check that your math is correct and that you set everything up and that everything is canceled like it's supposed to, because they will both point to the same limiting reactant. Okay, so in this case, I'm going to test my 1 slice of cheese. So I have 1 cheese. And the question I am asking is, okay, I have 1 slice of cheese. How much bread do I need for that 1 slice of cheese? Okay, so I know that cheese is the unit I want to cancel. I'm trying to predict how much bread I need. Of course, this is a 1-to-2 ratio, just like my balanced chemical equation. Oops, let's show cancellation here. And like you already know, I need 2 slices of bread for this. So if I'm going to use up all of my cheese, I need to have at least 2 slices of bread. This is how much is needed. How many slices of bread do I actually have? So this is what, again, my theoretical calculation, my test calculation. Okay, so I need 2 slices of bread. So I walk over to the pantry, I open it, and I say, how much bread do I actually have? Well, from the problem, you can see you have 3 slices of bread. So you need 2. You have 3. You have excess bread. So again, if you have excess bread, it means that your cheese is limiting, which we determined over here with our first calculation. Again, both of these calculations should point you to the same limiting reactant. So in this case, my cheese is my limiting reactant. Okay, I still haven't answered the first question yet, which is why these problems get really, really long. All right, so I know what my limiting reactant is. Once I know what my limiting reactant is, then I'm going to take my limiting reactant and I'm going to predict how much product I can make from that. But first I have to determine which one is going to run out, because if I start with my 3 bread or my 1 cheese, I'm going to get a different number of sandwiches for each of those. So that's why you determine which one is limiting, which one is going to run out first. So cheese is limiting. I need another page. As usual, I need another page. Okay, let's rewrite my balanced chemical equation. 2 bread plus 1 cheese gives me 1 sandwich. There you go. That looks a little bit better. All right, in this case, I know that cheese limits. So I'm going to give myself that note just so I know which reagent to start with. All right, so now I'm going to predict how many sandwiches I can make. So I need to start with how much cheese I actually have. So I need to go back to my problem. I have 3 slices of bread. I have 1 slice of cheese. So this is what I'm going to use to predict my products. 1 cheese. And now I'm going to predict sandwiches. So my cheese, I want it to cancel. This time I want to go to sandwich because I'm predicting product. And I'm putting in my mole ratio, which is a 1 to 1. And so I can make 1 sandwich. Which again, you already knew from the problem from the get-go, but this is mathematically how we work it out. These are the tools that you actually already have that we are going to apply to more difficult chemical reactions. Okay, so I know there was more to this problem. Okay, so how many sandwiches can you make? So we can make 1 sandwich as we already knew. Okay, do you have any leftover ingredients? So now we want to look at our excess reagent. And for this case, our bread was in excess. So yes, we do have leftover ingredients. We have leftover bread. Well, how much bread do we have left over? This is really easy because we've actually done all of the legwork for this calculation. Because to calculate this, we need to know how much bread we started with, how much bread we used, and we subtract the 2. So the problem tells me how much bread I started with, 3 slices. Okay, so what did I start with? I started with 3 bread. How much did I use? Or how much was used? Well, that is this calculation right here, down here at the bottom, right here. So when I used up my 1 slice of cheese, I ended up using 2 slices of bread. So that's how much I used. Okay, so how much I used? I used 2 bread. So how much is remaining? So we'll say remains. We have 1 slice of bread. And like that was super easy. I mean, hopefully this whole problem is super easy, but this is how we do the calculations. And again, this is where it's helpful if you have the time, if you're not in a situation where you're in a test or a quiz or a time situation, why it's nice to test both of your reactants. One, it helps you confirm that yes, you have chosen the correct limiting reagent, but also if you are asked later on a question about excess, then you have already done at least a big part of the calculation to determine how much is left over. Okay, how are we doing on time? We're running a little bit behind, so I feel like let's go ahead and take these skills and apply it to a real chemical equation because these are long and I'm definitely going to run out of time. But just if you're curious, here are part C and part D. If you want to run through these calculations again, as soon as you read it, you're going to figure out what the answer is. But see if you can write it down in a way that you would for a chemical equation and get the answer that you expect, because then you know that your method is correct and you can apply that to chemical equations. Okay, so now I'm moving on here. All right, so we've got our combustion reaction. This is again one that we balanced last week, or sorry, 2 weeks ago, I'm almost certain. We're going to do limiting reactant with this, but we're still staying in moles. Okay, so our first question here for A is how many moles of oxygen gas are needed to react completely with 3 moles of butane? If you have 40 moles of oxygen, which reactant runs out first? Which reactant is in excess? Okay, all right, so we've got, again, a couple of different questions here. What we want to do, or what I often do first, is identify the kind of question. And for me, the first thing I identify is this is a stoichiometry question. One, I have a balanced chemical equation. The second thing that tells me I'm dealing with stoichiometry is even for this first one in part A, I'm asked about moles of oxygen gas, but I'm given moles of butane. So I'm asked about one molecule, but I'm given information about another molecule, and I can connect those with a balanced chemical equation. That means we've got a stoichiometry problem. So for part A, I just have what I would call simple stoichiometry. I know how many moles of butane I have, and I want to predict moles of oxygen gas. But let's talk a little bit about the second part of the problem before we get into calculations. So the second one says if you have 40 moles of oxygen, which reactant runs out first? So now we've added more information into the mix. So now I know I've got 3 moles of butane and 40 moles of oxygen. So I have information on both of my reactants. That tells me I've got a limiting reactant problem. Of course, this last part here, asking which reactant is excess. If you see limiting or runs out first or excess or left over, that should also be a high sign that you're not just dealing with simple stoichiometry, but you're dealing with limiting reagent stoichiometry. Okay, so that's what I like to do first, is identify what kind of problem that I'm dealing with, so then I know what tools I need to use to solve this problem. So let's do part A first. This is just the simple stoichiometry. All right, so we want to know how many moles of oxygen or gas are needed to react with 3 moles of butane. All right, so we have 3 moles, sorry, this is part A, 3 moles of butane. And we want to predict oxygen gas. So this is like we did in the first part. I just want to make sure that my moles of butane cancel, and I'm trying to predict moles of oxygen gas. All right, so there are my units. Let's go to my balanced chemical equation and put in my mole ratio. So for my butane, I have a 2 in front of my butane, and for my oxygen, I've got a 13. Okay, so my mole ratio is 2 to 13. And this calculation gives me 19.5 moles of oxygen. Okay, great. So that's how much oxygen gas I need to react completely with 3 moles of butane. So let's go on to the next part. So now we're adding in the other wrinkle. So if I have 40 moles of oxygen, which reactant runs out first? Okay, well, I can actually use the calculation that I just did, because if I've got 3 moles of butane, I need to have at least 19.5 moles of O2. So if I want to react all of that butane, if I want that butane to be completely gone, I need to have at least 19.5 moles of O2. How much O2 do I actually have? Well, the problem tells me that I have 40 moles of O2. So I have so much more O2 than I need. So O2 is in excess. What does that mean? That means that butane is limiting. Okay, but let's test the other way as well. So this is if I'm going to use up all of my butane, but what if I'm going to use up all of my oxygen? So if I have 40 moles of oxygen and I want it to be all used up, how many moles of butane do I need? So this is going to be moles of O2 in the denominator, and then moles of butane in the numerator. I have a 13 in front of my O2, and I have a 2 in front of my butane, and this gives me, just 1 second while I try to figure out what 80 divided by 13 is, 6.15 moles of butane. Okay, so if I'm going to use up all of my oxygen, I need at least 6.15 moles of butane. How much do I actually have? So let's walk over to the pantry. And this is like asking, how much bread do I actually have? How much butane do I actually have? Well, I only have 3 moles of butane. I don't have enough. I am going to run out. So again, my butane is limiting. And this is exactly what the previous calculation also showed, was that my oxygen is going to have excess, and I'm going to run out of my butane, which is why I put it here in the box. So just another kind of tip off the top of my head, when you're doing these problems, make sure that you label your limiting reactant really, really clearly, because you don't want to go through all this work, correctly identify your limiting reactant, and then, oops, I used my moles of my excess reagent, because that's going to give you the wrong answer. So just make sure, however you think of it, make sure you know which one is limiting and you write it down. Okay, so butane is my limiting reactant. So that one is going to run out first. So butane limits. And then which reactant is excess? Okay, so oxygen is in excess. So those are the only two calculations that we actually needed for this. Were these two pretty simple calculations, but again, when you think about it conceptually, it can be kind of difficult. Okay, let's go on to part B. Okay, how many moles of water can be formed when 4 moles of butane react with 50 moles of oxygen? Which reactant is limiting? Which one is in excess? And how much of the excess reagent remains? Okay, so we need to figure out how much remains as well. Again, identifying what kind of problem this is. So I have been given information about 2 molecules and asked about a different one. So this is some kind of stoichiometry problem. I know it's a limiting stoichiometry problem because I'm given information about 2 of my reactants, and then I have to figure out which one, again, is limiting and which one is in excess. So it's nice to know what kind of problem we're dealing with. Of course, we're always going to be dealing with stoichiometry here, but when you're in a situation where you're looking at homework from mixed units, or you're getting ready to go into a test or a quiz, you want to be able to identify what kind of problem you're dealing with so you can use the right tools to figure out what's going on. Okay, so we have 4 moles of butane, we have 50 moles of oxygen, and we need to figure out which one is limiting. So let's start with our 4 moles of butane. And of course, you can start with your oxygen if you want. So I'm gonna run this test, and I'm going to figure out which one is limiting, and then I'm going to confirm it. So I have 4 moles of butane. The question I'm asking is, if I have 4 moles of butane and I want all of this butane to react, how much oxygen do I need? Okay, so that means I want my moles of butane to cancel. I am trying to predict moles of oxygen, so that goes in the numerator. Now to get my mole ratio. Butane has a 2 in front of it, and oxygen has a 13. And you know what? Because we've started a new problem, I am going to erase this because we haven't determined our limiting reagent yet for part B. Okay, so as always, making sure units cancel like they're supposed to. All right, this gives me 26 moles of oxygen. So again, the question that I'm asking and answering is, if all of this butane reacts and there is none of it left, how much oxygen do I need to make that happen? Well, I need 26 moles of oxygen. How much oxygen do I have? So again, you're walking over to the pantry. How much do you have? And based on the problem, I have 50 moles of oxygen. So I have excess. So that means butane, again, is limiting for this problem. I have excess oxygen, which means my butane is going to run out first. But let's test it the other way. So let's say you decided to test oxygen. Then you would say you have 50 moles of oxygen. If all of that oxygen is going to react, how much butane do you need to make that happen? Okay, so my moles of oxygen need to cancel, and I need to convert to moles of butane. This is getting a little crowded. This is going to be 13 to 2 again. Moles of O2 cancel this time. All right, so this calculation gives me 7.69 moles of butane. All right, so if all of my oxygen is going to react, if all of those 50 moles of oxygen is going to completely react, then I need to have at least 7.69 moles of butane. Okay, let's walk over to the pantry. How much butane do you actually have? Do you have enough? Well, I only have 4 moles of butane, so I do not have enough. So again, this tells me that butane is my limiting reactant. It is going to run out first, and I'm going to have oxygen left over. Okay, so that means which reactant is limiting. We've already identified that. That is butane, which is in excess, and that is oxygen. And then how much of the excess reagent remains? Let me get myself another page here. Let me write my balanced chemical equation. Okay, so we have a combustion reaction with butane, 10H2O. Okay. So this was again like the sandwich. I need to know how much, again, for excess is my O2, how much O2 I started with, how much O2 I used, and that will tell me how much is remaining. So the problem will tell me how much O2 I started with. So I started with 50 moles of oxygen. So here is start. I started with 50 moles of O2. All right, how much was used? I've actually already done this calculation. Woohoo! All right, so to react all 4 of my moles of butane, I used up 26 moles of O2. So how much was used? 26 moles of O2. All right, so how much remains? I just subtract them. So this is what remains. It is 24 moles of O2. So again, the nice thing about at least having the time to test both of your reactants is when you're trying to find excess, like a lot of that work is already done. It makes it much, much easier. And once again, I've got too many problems to do and not enough time. So that is how we do limiting reactant stoichiometry with just moles. And again, I know I keep repeating myself, but the main thing I want to point out here is that you have these skills to do this. You already have them. You actually already do this in a lot of different ways, not just making sandwiches, but like if you're planning a party, how many chairs do you need around a table? Do you have enough chairs? Are you going to run out of chairs first? Are you going to run out of tables first? All of these things are the same thing as limiting reactant stoichiometry. So you absolutely know how to do the math. You just need to take those skills that you do every day and put them in a chemistry context. But I promise you already know how to do these problems. So thank you so much for joining us for this live stream. I'm so glad that the audio was working, and I hope to see you guys next week. As always, if you have requests for what you would like to see in the live stream, just let me know and we will talk about that next. Thanks so much. Bye.